Okay, now that we're at the top of the hour, I think we'll get started. So hello, everyone. My name is Leah Oxford, and today's webinar is focused on how we can leverage the electrical digital twin for reliable power delivery. First off, just a few webinar logistics. If you have questions throughout today's presentation, can you please leave them in either the Q&A chat window or the chat box, and we will get to them after we have finished presenting the content. And just so everyone is aware, we have all put you on mute and we ask that you stay on mute throughout the session. And one final note, this event is being recorded and we will send out the recording after the session has been completed. So a few introductions today. As I'd mentioned, my name is Leah Oxford and I'm the Marketing Communications Manager for ABB Energy Industries. And today I'm joined by three speakers. Our first speaker is Steve Royston, who's the Onshore Oil and Gas Technology Manager for ABB Energy Industries. Also joining us today is Stein Trostheim, who's the Global Product Manager for Process Power Manager and Process Power Simulator. And last but not least, Elise Thurode, who's the Global Product Manager for Simulation and Digital Twin. And with that, I will pass it over to our first speaker, Steve.
Thanks, Leah. Yeah, I think I'll start our webinar today with a quick safety moment. I'm from the oil and gas industry, and so safety is very much at the forefront of what we do in the oil and gas industry, of course. And this is just a brief safety moment. These are actually two photographs that I took from a window in my house just the other week, and it shows a fairly substantial fire coming from what was a wooden garage. And really the takeaway from this safety moment is to be mindful of the fact that during the summer months these buildings can get very hot, and if you are storing hazardous substances in there, they can easily be ignited. So that the takeaway here is to please make sure that you adhere to your local regulations in terms of what hazardous substances and the quantities that you store in these type of outbuildings. With that, I'll move on to the agenda for the webinar, and thank everyone for taking the time to dial in and see the presentations that we're going to give. The agenda for today runs as follows, really. In the beginning, I'll go through the challenges that are faced by industry in terms of power management, and I'll follow that with a brief introduction to ABB's power management system solution that we call Process Power Manager, and a primer for those that might not be familiar with what power management systems do, followed by a description of what is the main topic of today, which is our life cycle simulated digital twin and our electrical dynamic modeling product called Process Power Simulator. And having introduced those kind of two main topics, I'll hand over the presentation to my colleague Stein Trostheim, who is the product manager for the Process Power Simulator, and he will go through a few case studies showing how we can use this product to bring benefit to projects and benefits to the end users. And then after that, we will open up the floor for questions and an open discussion with your good selves. So, what challenges are faced by the industry? One of the biggest challenges really is to make sure that that our industrial processes are fed with electrical power on a 24/7, 365 basis. And they need 100% availability in many cases, because the power being delivered to the process is critical to protect not just the production asset itself in terms of being used to start up and power, and shut down the process in the event of an abnormal situation occurring, but also to protect the environment and, more importantly, the people around it. Another challenge that our customers are facing today is the fact that there's a increased market pressure and certainly facing in the near future regulatory pressure on end users to lower their overall carbon footprint and lower carbon emissions. And an example of this is offshore, where offshore operators are looking to use offshore-based wind farms to replace, for example, aeroderivative turbines driving power generators on offshore fixed platforms. And the other challenge faced with this embracing of renewable, sustainable power sources is that some of these power sources are not available all of the time. And so we need to mix these in with traditional power sources, and this significantly increases the number of sources that we have to deal with in our power management system solutions. And also, we have to be cognizant of the fact that there are a lot more large loads being driven by semiconductor converter type units like variable speed drives. These can often be used to also lower emissions by tailoring the amount of power delivered to the load. But in turn, these units are more sensitive to the characteristics of the power network, which means that the power management system has to handle a more complex situation and increased complexity for the distribution system itself. What can we do to help our customers tackle these challenges? One of the ways we can do this is to build an electrical digital twin using our Process Power Manager product and the Process Power Simulator. And I'll go on now to explain how we can do this. Before I start, I'll give a quick primer for those that may not know what a power management system normally does. And for this, I will use an analogy with a train analogy. And in this analogy, a lot of our customers have their own power generators connected to their own private power distribution network, which may be completely disconnected from a public utility, for example, and run in what we call an island mode. And in this analogy, the locomotives at the front of the train represent the power generators that are delivering power to this network. The speed of the train is analogous to the frequency of the power supply in the network. And very often, most electrical equipment is set up to automatically trip if the frequency falls below a certain level. So it's very important to keep the frequency at the right level in these power distribution networks. And the wagons connected to the locomotives are a representation of the loads that are connected to the network. And in this analogy, the wagons, the white wagons that are connected to the locomotive in the first instance are what we would call the critical wagons, so the critical loads, the ones that we need to deliver under all circumstances. And for the reason for explaining this will become apparent on the next slide. So we deploy our Power Manager, the Process Power Manager solutions to provide functions to control and automate and keep the power applied to all of the critical loads. And one of the things that I mentioned earlier is that it's crucial that the locomotives travel at the same frequency, at the same speed to maintain the frequency on the network. But of course, the locomotives may not necessarily deliver the same amount of power So some of the locomotives may be more powerful than others, and they will normally have to share the load. And one of the things that a power management system solution can do is that with the functions I'm going to describe, one of the benefits are that you can effectively reduce the amount of locomotives you might need to couple to the train in order to ensure that it reaches its destination. If one of the locomotives suddenly fails, then unless we do something, the speed of the train will drop and begin to fall. And this is analogous to the frequency effect of the frequency on the network if a generator trips. And what we can do under those circumstances is to effectively decouple the wagons. So we have to decouple enough wagons to compensate for the loss of power due to the engine failure. And this is a process that we call load shedding. And in power management system solutions, we do this load shedding extremely quickly using digital outputs hardwired to the trip relays on the circuit breakers, or we might send the commands to the protection relay using an Ethernet protocol called IEC 61850, which can transmit the load shed command in a matter of milliseconds. The other function that a power management system may provide is the need to synchronize. And what I mean by this is that if we want to add another locomotive to the train whilst it's running along, we have to match the speeds of the locomotives in order to be able to couple them up. And this is particularly true if we want to connect the network to a public utility grid, which kind of represents an infinitely large locomotive running along the line in front of us. We will have to synchronize our speed with that locomotive in order to couple onto it. And that's kind of how we would explain the process of synchronization. So installing a power management system solution is crucial to keep the power to the critical loads under all circumstances. As I mentioned earlier, ABB's power management system solution is called Process Power Manager. And the product contains a number of applications that can be configured to provide the functions I described before, such as power control and load shedding. And the product is designed to be integrated into a System 800XA automation system solution. And the applications work together in an integrated manner in order to make sure that the power network remains in place to the critical loads in the event of disturbances such as maybe a power generator trip, as I explained through the load shedding function. And the solution provides the ability for plant operators to view the entire electrical system through a number of interfaces to various equipment items like motor control centers, transformers, intelligent switchgear, and to the generator control systems through a number of different interface types like Modbus or Profinet, Modbus TCP, etc. So that's really a quick overview of our power management system solution. As I mentioned before, our Process Power Manager is designed to run on a System 800XA automation platform. System 800XA is ABB's flagship automation product, and the XA stands for Extended Automation, and it's much more than a DCS because it contains the fully integrated capability to provide asset management and long-term data historian functionality, as well as the ability to integrate other systems, third-party systems such as telecom systems like CCTV surveillance systems. But the other thing that System 800XA is able to do is to also provide process control and safety functionality, process safety functionality such as emergency shutdown and fire and gas functionality. And we can combine that functionality together with power automation in one single solution with this approach. Process Power Manager has a number of user interface elements, allowing us to build a user interface that's based around the dashboarding kind of concept. And the reason for this is that most of the decisions that a plant operator has to make when it comes to power management are normally very fast decisions. And having a user interface that's based on kind of dashboarding technology means that all of the important information is delivered to the user of the system in a very clean and crisp, concise fashion, without having to browse through too many pages or look at too much information, and is also very much based off the good practices that we employ in the process and safety industry in terms of user interface design for abnormal situation management. So to summarize, our power management system solution will deliver fast-acting blackout prevention in the event of a generator trip by fast load shedding. It can ensure that power is delivered to the critical loads, and it will minimize the amount of load shedding it has to do in the event of a failure, so that you don't unnecessarily shed too much load. And one of the advantages of our system, which you can't do on a train, is that you can actually shuffle the wagons about whilst the train is still moving. So in other words, we can change the load shedding priority matrix on the fly, if you like, so that if for some reason we have a process condition change, we can change automatically the priorities of the load so that they get shed first, whereas before they would have been shed later. So we can do those changes, which is not possible to do, obviously, on a real train, if you like. And then also we have applications in there to manage the synchronization of the power sources, and to control the active and reactive power control, and to control and automatically balance the loads between the generator sources. Having explained our power management system solution, I'll do a brief introduction of our process power simulator. As I mentioned earlier in the discussion, we're in the business of supplying process control and safety automation system solutions, and quite often we're supplying those with a fully integrated power automation capability as well. And when we quite often when we supply process control systems, we're also asked to provide an operator training simulator. And the operator training simulator uses a dynamic process model, often supplied by a third-party vendor, such as Chorus in this example, but there are many different vendors for high-fidelity process models. But as in ABB's case, because we're providing integrated power automation as well, we have developed the process power simulator to add dynamic simulation for the electrical world to the dynamic simulation provided for the process. And this is what we mean by completing the digital twin. For those of you that might not be familiar with operator training simulators, there is traditionally a lot of these simulators are what we would call emulated simulator types. If you look on the left-hand side, we have the real-world production control system, which is performing the process, safety and power automation logic that I've described before. And on the right-hand side, in a typical emulated simulator type, the vendor of the simulator will produce a mimic of what is in the real-time production system, but using a different coding mechanism. And because they're using a different coding mechanism and trying to emulate what's going on in the real world, sometimes these two are not completely 100% identical. So there may be differences between one and the other. And Keeping them in synchronization is quite often a difficult task because on the left-hand side, when you're commissioning the system and making the most changes to the real production system, quite often at the same time, you are also training your operators on the simulator to be ready for when the plant is available for operation. So right at the time when you're making the most changes in the real world, you want to reflect those changes across to the simulator world. And that's quite difficult with an emulated system because you're using different coding mechanisms and making changes can take time. And often in these traditional emulated simulator types, the electrical model does not even exist in those solutions. ABB's simulator is called we call it a life cycle simulator, and I'll explain the reason for that in a few moments. With an ABB life cycle simulator, on the right hand side, it's based on a complete virtualization of the real-time production system. So we have virtual controllers in the system, and they run an identical copy of the application software that runs in the production control system. And we have the ability to virtualize not just the process and power automation controllers, but we can also virtualize the safety controllers in this simulator. And we can run that against the process model, and we can also run the simulation against an electrical model with the process power simulator, so that we can not only emulate what happens in the process and the feedback coming from the valves and the motors, the open and closed feedbacks. We can also simulate the frequency and the voltage and the currents in the power distribution network, and also the responses that we would get back from the protection relays with regards to whether a circuit breaker is open or closed, or whether a generator is running or not. The real benefit, though, of having such a simulator where we're emulating the real system is the fact that we can dump out the control logic from our programmable controllers, and we can dump out the HMI graphic displays from the real-time production system and load them straight into the simulator system. And this is because we're effectively running the same firmware in both environments. And the process of dumping out from the real world system and loading into the simulator is extremely quick. There's no new coding to be done in the process. And the other major benefit of this is the fact that this is a bi-directional capability, so that we can actually dump out the applications from the simulator environment and load them into the production control system. So this means that we can use this simulator for operator training, but that we can also use it for engineering purposes. And this means that we can use the simulator to engineer our applications in the simulated environment, and we can test these against the process and electrical model. And when we're satisfied that they're working correctly, we can dump out that application software and load it into the real-time production control system. And this is why we call it a life cycle simulator, because we can use this at all stages of the project. We can use it for doing studies during front-end engineering design work. We can use it to check out our DCS configurations during the engineering process. We can use it to train personnel, and we can use it to investigate optimization while the plant is in operation. If changes need to be made to the real-time control system, we can do those changes on the simulator, and we can test them out and make sure that they don't affect the existing operation when they're deployed. And when we're satisfied that's the case, we can dump those applications out of the simulator and load them into the production control system with a higher degree of confidence that we won't cause any abnormal situation to the already running plant. So just to explain briefly the process power simulator product, it's a real-time simulator for power systems. It contains dynamic models for typical electrical components such as generators and the bus bars that you would find in medium and high voltage switchgear. And it has interfaces, it has the capability in there to mimic and provide a source of data for interfaces for control and measurement. And it also is highly scalable, so we can use this model to use this product, I should say, to build models for very large scale plants, such as in a typical kind of gas to liquids plant. On a very large plant, you might encounter several hundred protection relays on medium and high voltage switchgear distributed over maybe 20 substations, and with maybe 12 generators connected to the system. And the process power simulator has the ability to produce a dynamic model for very large systems as well as the smaller ones. As I mentioned earlier, there are several use cases, and my colleague Stein will go through a few of those in more detail when I've finished with this section of the presentation. But it can be used for electrical studies very early on in the project phases. We can use it for virtual factory acceptance testing of our power management system solutions, and we can use it for operator training. And of course, we can integrate the process power simulator together with a process model to provide a very realistic and complete digital twin that's truly representative of what we're controlling in the real world. And just to finish up with a description of a few of the features in the process power simulator product, we have what's called a topology editor. This is a graphical user interface that can be used by the person that's going to build the electrical model. It's a graphical interface with drag and drop technology deployed, so you can build up your dynamic model in a single line diagram type basis and drag and drop the various electrical equipment items that you want to model onto this single line diagram, and it will create the dynamic model from that graphical user interface. The product's equipped with a number of reporting tools, because whilst you're running the simulation, you may want to log many values and produce reports and kind of to log the results of the simulation. And it also comes with two interfaces. One interface, which is the operator interface that would be used during an operator training scenario. And the other interface is a simulation user interface, an instructor station, which is based on the topology editor. And this gives a user interface to the instructor so that the instructor can set up various scenarios for the operators during the training sessions. So that's a brief overview of our process power simulator. What I'll do now is to hand over the floor to my colleague Stein, and he'll go through a few of the case studies that we have to present today, where we use process power simulator to provide benefits to our customers. And over to you, Stein.
Thank you, Steve, and welcome to all of you. We'll go through 4 different case studies or projects we have participated in. And the first one is the introduction of wind turbines into an oil-producing platform, or in reality it's two platforms connected with a cable, and one of the platforms have the wind turbines connected to it. So this is one of the first kind of island mode type usage of the wind turbines in the oil and gas industry. So the purpose with it is to utilize the wind as much as possible and turn off as many generators as possible. And of course, the challenge here is to cope with different production scenarios and wind scenarios and other types of disturbance, and how to manage start and stop of the generators, or when to start and stop, and wait as long as possible before starting up a generator, just to be sure that the emission requirements are met. So with this project started up in the concept study, where we draw the model, put up some basic and use some basic standard configurations of each of the components, and then added on more and more information as long as we went in the project. But the purpose here was to have and establish a coordinated control and test and verify the control philosophy on the plant. So with this, we studied how the voltage, how the frequency, and the flow of reactive power was moving in the system, and how to utilize tap changer control in order to control some of this. After this has been completed, now we are moving into the next step, where we have the model available, and now the customer can build their control logic, or we can build the control logic for the power management system, and then hook it up to this simulator now. So we are actually building the control logic in an 800XS simulator environment, so we can test out as long as we go here. For example, let's test load shedding, let's test power control, and so on, and then make the necessary modifications. So the system in next phase is moving over to FAT and commissioning, that everything is prepared and tested thoroughly to handle all the different scenarios. When we create these scenarios, we can kind of retrofit them, or do retrospective tests during test of the control system. So everything can be reused later on for testing, and also for operator training, how they will manage this new situation on board, which is very different from their current situation. So I think this also unlocks performance in the system, and will also help to reveal other weaknesses, or make sort of additional improvements to either operational philosophies, or improved regularity and on the plant. We can move on to next, Steve. Yeah, so here is another type of case. It's an LNG plant. The aim here is to perform FAT on the power management system and the electrical control system. So basically, you have the ability now to do much more detailed testing and more advanced testing than traditional IO testing or traditional feedback testing without any dynamics in the system. So that was sort of the purpose with it, to do the FAT and finding either faults in the control system or the application, and tune that application to meet the we call it the adequate response to the different disturbance they introduced here. Another thing was the tuning of the generator interfaces. So our power management system is sending discrete control signals to the generator. So by tuning up the generator and parameters in the model, we are able to have a very realistic dynamic response of that generator. So when you kind of introduce and you start a load, the generators will respond as they would have been in the real plant. So we were able to tune that regulator and interface exchange, and timing of how long the pulses are and how short they shall be, and so on, in advance of commissioning. So this really reduced a lot of site activities, and also I would expect to spend less time on load test for the generator, and we are always kind of the last people to participate in these types of tests. Especially also doing load shedding tests is almost impossible to do on a live acting plant, and even during commissioning it has some limited purpose actually. Even if you test something, you will get the answer when the first disturbance is there, and then we can utilize the simulator now to perform all that actions and see what the response is on the frequency, voltage, and the important parameters there. So we can move on to next, Steve. So this is another example of an upgrade where the customer required us to do a new FAT after the upgrade to make sure that the application is working as it was before the upgrade. And it is actually simpler and quicker to set up a simulator of this type and build a model, and you don't need to have everything included. However, medium voltage is typically something that should be included, and also your sheddable loads, where are they? Are they in low voltage or medium voltage? So you don't need to represent everything, but by doing it's so simple to actually build the model, and it's very quick to do it, and it's actually quicker than setting up a test system with IO testing and feedback logic for this case, and you get so much more out of it. So what they discovered during this testing period is that they were not able to test all the scenarios with the traditional way. And so they discovered that there were several trip limits which needed to be fixed, and they were actually wrongly configured in the application, which could have led to a blackout situation or a huge overload shedding, so to say, shedding too much load under such a condition, causing a process stop. So this was corrected. I think it's also worth mentioning that we can now, these guys, they rented it for 2-3 months, I think, and did all the testing there, and so it's a possibility to rent the simulators also, and if you select to do that. Yes, we can move on to next, Steve. So this is a case where we did the testing of can we really interface a process model? Can we really make a plant simulation, including electrical process safety? And we did a test with a company called Coris, but the principles are the same for other model vendors. We exchange data through OPC, and in this case, if you send a start signal, it will actually go to the motor that spins up, and then we are reading the torque values. We are sending the RPM signal up to the process model, the pump, and the pump responds with a torque value, mechanical torque value, which we are sort of feeding back into our motor, and then it's responding in that way to the torque, and the torque is sort of into electrical current, and that is sort of making that motor spin up. So in the curve here, you can see that the red one is the active power consumed by the motor during that startup transition. The yellow one is the RPM, and the green one is the torque value coming from the process model. So it's really simple. It are not many signals that is required in reality. So with this we are able to run both the electrical and the process models together, and combining it with a real simulated control system application. So that was my short presentation here. So I leave it back to Steve. I think, Steve, you have to unmute.
Thank you, Stein. Yeah, just before we open up the floor to questions, I'll just do a very quick summary here. We believe that by producing the process power simulator, we have created a complete digital twin to complement our process control, safety control, and power automation integrated system solutions. And we combine that with the fact that we're embracing new technologies such as IEC 61850, which allows us to interface with intelligent electrical devices using Ethernet networking techniques, and we can not only use that to send very fast tripping commands to the circuit breakers for our load shedding functions, but that we can also use it to gather significant amounts of diagnostic information with which we can feed our asset management capability in System 800XA. We have a global, a very large global support network that is familiar with the functionality of a power management system solutions, and we can combine this with a very deep energy expertise with a lot of years of experience in delivering integrated process control and safety system solutions together with integrated power management functionality. So that kind of concludes our webinar, and I'll just hand over to control back to Leah, and she can orchestrate the question and answer session.
Great, thank you, Steve, and thank you, Stein, for your presentation as well. So I ask that as we go through some of the questions that are currently in the Q&A box, that if you have any more, please type them and we will try to answer them in this call. So the first question, is this a competitor to ETAP, or is the PPSIM used to supplement a software like ETAP?
I can answer that. We don't consider PPSIM as a competitor to ETAP. ETAP has been there for a long time, and it's probably a very good tool. However, the principles of PPSIM is that we are running real time, and very large system is possible to integrate here. So in principle, you can take your whole refiner and put it in here, and then get the dynamics out of that. I think also we are, the purpose of it is to test the control, the real control application, and that you have to have the ability to connect to a simulated control system like we do, which I don't think ETAP has the purpose for. So so that is another sort of a differentiator here. We can also import data from, for example, if you have already ETAP, you can send, for example, the equipment data and so on, and also the response data from the generators to us, and then you can easily implement and update the simulator with these characteristics. So that is, we've done that several times. When it comes to reality, and I think we are equally good to represent a generator than any other type of model in the market. Also comes to motors and transformers and so on. That is what we have seen, and we have done a lot of thorough testing on other projects to compare these tools. But however, I don't consider it a competitor, since ETAP has other functions and than we can provide. So it's more like a supplement, you can call it, yes.
Okay, great.
And it doesn't require that much competency actually to set up. So we have tried to make it as user-friendly as possible. However, the model can be as realistic as in the real world. So that has been the purpose of it.
Okay, another question around cost. So to get a digital twin model performed, what is the typical capital investment in terms of equipment and then analysis? I'm not sure if we have a case example that we could maybe.
Yeah, I think we can. Yeah, so the efforts to build the model doesn't take long, and I think we are in the category around $200,000 for this type of electrical simulator, depending how big you want it, how many loads you want to include, and so on. And then you also get the 800-axis simulator part, where you can have your electrical control system from ABB included on. For the PPCM as a standalone, the price is different, much lower than that, and if you want to hook it up against, for example, another type of vendor, which we can do, we are using OPC here. The only requirement is that the other vendor for kind of stimulated or emulated control power management system need to be speaking OPC, and they have to be OTS, operator training simulator aware, meaning that you can freeze and store a situation, you can upload it again afterwards, and then play it from there. So that is the kind of the quick way we do operator training, and also performing FAT, that you just run a scenario, and then you click on two things, and you're reverting back to the initial condition you have saved, and then you play it all over again or do something else. So it's a very quick way of doing a lot of tests in a short time period.
Okay.
So yeah.
Next question. So does the process power simulator work with any make or supplier power generation system?
Yes, work with any make or supplier power generation system.
The generators?
Yeah. That it doesn't. Yeah, okay. Well, we can represent any type of power generation system. It is generic, and the same for the process power manager. Can interface any type of a generator, if it's solar, GE, if it's a steam turbine, diesel generator, whatever. So it is sort of generic in the way we interface them anyway.
It's configurable.
Yeah.
You can change the parameters, the characteristics of the generators. We have default settings, so that can be changed to adapt to the specific generator that is used.
Yeah, so you have both the response of the governor, and AVR can be configured to meet the plant configuration. Of course, you need, and every model needs some step responses in order to tune them in.
Okay, and another question around, well, I guess this is our first question around CO2 emissions. So can the digital twin model determine a reduction in carbon emissions, or does it have this possibility?
For sure. Especially in the early phases of the project, before you even start considering what type of motors, engines you're going to buy. it's so much easier to do this with a simulator and simulate and make the right selections. So you can dimension your motors and VSD according to more average process flow or a process sequence instead of peak demand all the time. I think what they say is that you can save up to almost 30-40% actually on some right motor dimensioning. We have done some experiments earlier that we saved up to just a small quick exercise with a process model. We were able to replace the pump and the VSD and had a savings of around 20% on capex for that 200 kilowatt motor, and also 10% on the OPEX reduction, which is sort of equivalent to CO2 emissions. So yes, I think we can, but if you want to really dig into CO2 emissions also, you have to look into your process, how it's sort of the process optimization and tuning of that one, especially on heat consumption, which is requiring a lot of power. So yes, I would say that the digital twin here can be really exploring that possibility.
Especially if they want to see what to change in the process, it would be good to look at the simulator first to see if the changes are too costly or not, if it is a good investment. So
yeah, it is kind of a, if you want to attack the energy reduction, you have to attack it everywhere. So it's not only one place. Maybe you don't want to replace your big motor out there, and but then you have to look in other places. So it's a kind of, but you have to have the KPIs here to monitor, to make sure that whatever you do is monitored against the key performance indicator like energy intensity and so on, and how much energy are you producing, and combined with your product, how much product is coming out in the end. So but definitely the simulators are unlocking this performance.
All right. Is the process power simulator able to be integrated with other process automation systems?
yes, as Stan mentioned, we are communicating between the process power simulator, the model, and the control system via OPC, DA, or UA. So we can interface any soft controller, so to say, of other automation systems, as long as they can communicate the IOs, and also that they can synchronize, like Stein mentioned, that they can have the simulation commands to load the snapshots or initial conditions, so to stop and start. So that can be done.
Yeah, I think also Honeywell has a model, right? Process model, and they can also do, I don't know if they do emulated control or not, but
they have.
Sure, yeah. So, and also they have OTS functionality.
Yes, certainly. And what we've seen also that we don't necessarily need the control system, for example, in the beginning. So it's possible that process power simulator can communicate with the, for example, Honeywell model, and then you can look at the process and electrical dynamics together before implementing the control system.
Great. There's a bit of an extension to this question. Is the simulator able to only simulate ABB products, or could it be simulated with other supplier data too? How do we export the other data into the model?
Well, you can buy any type of third-party product, and like motors, transformers, generators. All they have the same data sheets in basically. So based on the data sheets, for example, from a motor, we can just import that data into the simulator, and then we have the the correct representation of it. So it is basically a very good standard out there. What are the different types of values we need to get from a supplier? So yes, it's any type of product.
Okay. I think this further, I mean, same line of thinking, but is it possible to customize the process power simulator?
If you want to make, yes, there are some customization, but so basically you change the parameters in order to adapt to that equipment. But if there are special equipment we don't have in the library, we will have to develop a model for it, and that can be done. And I think that is something we are looking into for future expansion, also to have customized objects here. But currently, we think we have most of the most common equipment. Oh, and of course, there are a few more which will be introduced in the next revision of the product. So there is not, the user don't have to program. He has to just drag and drop and configure the parameters for each object. And that's the sort of the simplicity we have introduced into it. Otherwise, it requires much more competence in order to program, for example, a new type of equipment, which is you need to be a very understand a lot. So and all the faceplates for the instructor is there, so you can operate it like you are in front of the real equipment. And there is also pre-made fault conditions included in these faceplates to create a disturbance or an operator training scenario. Of course, there is with the scenario maker we have is more freedom to set up different types of scenarios and manipulate input output there to create that specific situation you want to test.
Okay.
So yeah.
And is there a minimum for data points that is required?
You have to have the nominal values, like how big, how many megawatts, what is the nominal power and the frequency, basically, in many cases. That's a good starting point. And with that, we can use the standard setup, or there are some templates you can use here to load up. For example, that I have a diesel engine. Okay, then you select the template for a diesel engine, and that fills out the parameters for you. So basically, you can go with the basics, and then you can go more advanced to get more closer to your real equipment if you like to. But depending on the purpose of the test you're going to comply or do, I would say that the generator is the most important one, because that's where you have the response. That is where if you start a big heavy consumer, that one also have to have the big consumers, the big equipment needs to be more realistic. I would say the more low voltage motor, it doesn't affect the dynamics in an electrical network that much. So yeah, so it's not many data points you need in principle. So that has been the whole purpose with it, to really be quick setting it up. Don't spend that much time in building the model, connect it with the process application, and then start testing it.
Okay, and it looks like we have time for one final question. Can the simulator be adapted to a brownfield installation?
Yes, and some of my case examples was a brownfield example, and it is a sort of a yes, you can do that for sure. That was the purpose of it also, to really build it quickly and then use it for testing, and then also for operator training and all the types of purposes here, looking into energy, looking at how you utilize your how much utilization you have on the motors and so on. So it can give you a good overview of that situation.
No, so it's when you have the simulator, you can use it for different purposes. So, and for example, there's a question about if it is valuable for brownfield, justify the capex. We know that some sites, they do not, the operators have not seen load shedding for a while. How can they trust that it will happen in a correct way? So then you can actually avoid blackouts, because operators, they trust the automation system and the level of automation and the power management system. So if you look at the cost of a blackout, how that would affect the production, it could be very valuable.
Okay, perfect. Well, thanks to everyone, especially our speakers today, and we appreciate everyone that dialed into our session. There are some questions that are still in the chat that we will get back to each of you on if we weren't able to answer them today. And we will send out the recording shortly. So thank you, and we hope to see you on more of our Tech Talk webinar sessions.
Thanks for now.
Thank you.